Good day, everyone. Welcome to the second session of Drought Indices and Indicators, and today, a drought monitoring toolbox for the Northeast as presented in the aftermath of 2 years worth of research from the following groups: the Drought Research Institute, DRI, the Cooperative Institutes for Research in Environmental Sciences, or CIRES, CIRES, the Northeast Region Climate Center, NRCC, and NOAA's National Integrated Drought Information System. My name is Sylvia Reeves, and I am the NIDIS Northeast Region Drought Information Coordinator. Co-hosting with me today is my NIDIS colleague, Adam Lang, who is our Communications Director, and he will be running the show behind the scenes today. NIDIS leads a multi-agency partnership that coordinates drought monitoring, forecasting, planning, and information at national, tribal, state, and local levels. Today's presentation is the second of 2 webinars highlighting one of our many research projects and focusing on improving our drought early warning capability. So thanks for joining us. We'll get started with our presentation shortly, but I'd like to make sure that everyone is aware that in today's webinar, we will be following some slightly different rules than we did last week with regard to questions and the chat box. You should also know this webinar will be recorded and it will be made available within a few weeks, either through an email notification, or you can always go to drought.gov, the Drought Information Portal, to find that recording after we're done today. Adam is going to be monitoring the chat box along with me, and we want to make sure you check it frequently for any links to additional information. Also, you can put your questions or statements in the question section of the toolkit, which is on your right, for communicating back and forth for this webinar. So again, put your questions and thoughts into the questions panel and monitor the information coming from us in the chat box. So now that we've gotten our guidance for questions and chat straightened out for today, I'd like to introduce Dr. Dan McAvoy, who is the Regional Climatologist at the Western Region Climate Center and the Desert Research Institute. He'll take a few moments to introduce his team, share an overview of the Coping with Drought project, and he'll highlight our agenda for today. Dan, all yours.
All right, thanks so much, Sylvia, for the introductions. I really appreciate that. And let me grab the screen back here. Okay. All righty. So before we get into the presentations on the tools today, I just want to briefly cover why we're having this webinar today and why everyone's here. And so we're wrapping up a 2-year project that was funded through NOAA's Climate Program Office, the CPO. And we wanted to share, first, last week we shared some of the research highlights, and then today we're going to focus more on how to access some of these drought indices, maps, and data through some of the tools that the team has developed. So first, I do want to introduce the team here. So I'm the PI, and then we had a group from CIRES and NOAA's Physical Science Lab in Boulder, Colorado. We had Imtiaz Ringwala, Heather Yoakum, and Mike Hobbins, as well as my graduate student, Shuang Zai, who presented last week on the relationships between drought indices and crop health. And then we've also been working with Sylvia and Art from the Northeast Regional Climate Center and the Northeast DEWS. So this was a big collaborative effort. So Sylvia briefly mentioned about NIDIS. I did want to mention a few more things about these DEWS, the Drought Early Warning Systems. And so this is a map of all of NIDIS's different DEWS regions.
Hey, Dan.
And, yes.
We are just seeing the slide deck with the slides on the side. We're not seeing it playing.
Okay, thank you. Okay, let's see here. How about now?
No, we're seeing that slide now, but we're still seeing it on the side. Try play from current slide, maybe.
Is that any better?
Nope.
Let me try a couple more things here. Sorry, everyone. How about now?
No, maybe try closing it out again and opening it and see if that works.
Yeah. Okay, let me see here.
Yep, there we go.
Okay, let me just make sure you're seeing it progress through.
Yep, perfect.
Okay, apologies everyone. After all these months or now years of this, we're still having technical difficulties. So let me get back into the drought early warning systems, NIDIS's drought early warning systems. So this map on the right has all the different regions, and the Northeast region is one of the more recently established drought early warning systems, and this came about after or during and after the 2016 drought, when there seemed to be a bit of urgency for better monitoring and understanding of drought conditions in the Northeast. And so that's where the Northeast dews came into play, and the work that we've been doing is really to just help understand which drought indices and indicators and data sets really work best to help monitor these drought conditions in the Northeast. So we did have a few main objectives. On the research end, it was to identify the most effective drought indicators for hydrologic and agricultural drought monitoring in the Northeast. And this got into the different timescales of drought and how they relate to impacts, which indices or indicators, and that varied from atmospheric variables to land surface variables. And then the last bullet is talking about incorporating this into the Northeast dews and the management and planning. And so a lot of that comes from being able to access the data and the visualizations through different tools. And again, that's going to be the focus today. So last week we covered a couple of different research topics, one of them being the relationship between drought indices and crop stress. That was presented by Shuang Zai, who did a great job, and he talked about a lot of different indices and showed a bunch of maps and time series, and so we're going to show you how to access some of that today. And same thing with snow drought was another topic that we covered, and learning about how temperature drives a lot of the snow droughts in the Northeast. And we also talked about flash droughts as well last week. But the focus is going to be shifted today from what we learned in the research to learning about some of the tools that have been developed by the team and how to access these tools and the data that comes along with them. So I'm going to start off with a presentation on Climate Engine, and then we'll turn it over to Mike Hobbins for the Evaporative Demand Drought Index. And finally, Imtiaz Ringwala will present on the Landscape Evaporative Response Index, as well as the Drought Index portal. So I am going to shift presentations now, and hopefully this will work. Okay. Are you seeing the full screen mode, Adam?
Looks good.
Okay, great. All right, yeah, so I'm going to start off with the Climate Engine presentation, and this is doing a collaborative development between DRI and University of Merced, California, along with a lot of support from NIDIS. And this first map is showing one of the data sets that we can access from Climate Engine, which is MODIS's land surface temperature, and I'll discuss more about that. So before I go any further, I do again want to acknowledge the Climate Engine team. This is my role in Climate Engine has been very minor compared to most of the folks shown here. Justin Huntington is the PI of this project. He's a hydrologist from DRI, but the developers, the software developers, there's a whole team, 5 of them here that have really done the heavy lifting on developing this tool. So let's get right into it and talk about the Climate Engine web application. The main website is here, and I think Sylvia, if she didn't, will be putting this link into the chat as well. And so what Climate Engine is, it's a point-and-click web application, and it's powered by Google Earth Engine. And so this uses Google's cloud, and I think most people are familiar with some type of cloud application, whether that's Google Drive, Dropbox, Amazon Web Service. These are all cloud-based data storage where you don't have to store any of your data locally, and it all lives on these data farms in various different places, so you can access that information without the data being stored locally. And this screenshot here is the main web interface, the mapping interface. And so Climate Engine hosts various gridded climate data, remote sensing, and recently we've added some sub-seasonal climate forecasts as well. Most of the data sets are updated daily or in real time, whatever the timestamp of the data is, whether that's daily, monthly, something like the US Drought Monitor, that's weekly. And a lot of these data sets are global. And so we also have the 2 main features are mapping or time series options. And I am showing the US Drought Monitor map here from August 24th. And so this was a data set that was recently added into Climate Engine that you can access. And so this is a Google Earth type of interface where you can pan and zoom in and out. There's a transparency bar where you can see what's the underlying map as well. So what data sets should you use in Climate Engine? So when you get in there, you'll have on the left there, you'll see all these drop downs. And so we have climate data. There's a big list here with different climate variables. Then we have some precipitation focused data sets, snow-based, drought monitor, land surface models. Then the other main option is remote sensing, which is primarily the Landsat and MODIS archives, as well as some others, including Sentinel and some other products in there. And I also mentioned we recently added the subseasonal forecast data from Climate Forecast System, as well as NOAA's Forecast Reference ET and the Canadian Drought Outlook. So that is a long list of data products, and it would be hard to come to Climate Engine and really know, what to use unless you specifically already kind of know what you're looking for. And so what I'm going to do is walk through some of these products that might be most useful for drought monitoring in the Northeast. So I want to start off with the GridMet drought indices. And GridMet is a daily gridded product that was developed by John Abatzoglou at the University of Merced. And so this product extends back to 1979, and it includes temperature, precipitation, wind speed, downward shortwave radiation, humidity, and several other variables at daily timescales, which is a great asset for drought monitoring. And on Climate Engine, we have some of these in drought index form, including the standardized precipitation index, which is just precipitation, the standardized precipitation evapotranspiration index, which looks at the balance between precipitation and evaporative demand, and then just the evaporative demand drought index, which we'll hear more about from Mike later, the EDI, as well as the PDSI. And so with Climate Engine, we have some preset timescales available from very short sort of timescales that you might use for flash drought monitoring, like 2-week and 1-month timescales, out to very long timescales, 2 and 5 year, that reflect the multi-year drought conditions. And aside from the preset, you can create custom timescales if you want. Some people are interested in some odd number of days that they are interested for a certain drought, and they can compare that to all the other time periods in the record. And so I'm showing here the 2-year SPI from GridMet, and this is from August 23rd. And so we can see some of these lingering red, these darker reds in parts of northern New England, which shows lingering 2-year drought conditions there. So in addition to the drought indices, you might just be interested in the climate anomalies themselves, the raw values expressed as anomalies. Some of the ones for drought would probably be precipitation, temperature, evaporative demand. We have vapor pressure deficit, dew point, and wind speed in there as well, which we use those for the evaporative demand calculation using the Penman-Monteith. And so on the top right, we have the precipitation percent of average, and we have options for last 7 days, 15 days, 30 days, etc. Or you can customize your period. And I was putting these together last week, and there's usually about a 2 or 3 day lag. So if you went on there today, you'd probably get GridMet data from about 2 or 3 days ago. And so we see the precip percent of average, and then on the bottom right, the mean temperature anomaly for the same time period. And then on the bottom left is the vapor pressure deficit. And you do have the option to express this as just a straight anomaly, a percent of average, or a percent difference from average, because some of the variables might not, the percent of average doesn't work so well for something like vapor pressure deficit, because the values are so small. So you can look at the percent difference from average to really see that some of these higher vapor pressure deficit areas align with the drier precipitation areas. So yeah, the GridMet tools are great, but one limitation of them is they have a shorter period of record relative to some of the other data sets out there. So as mentioned, that went back to 1979, but we also have the monthly Prism data that goes all the way back to 1895. So you get a much longer period of record when you're looking at things like percentiles or the SPI. So we currently have the percentiles in there for precipitation, and hopefully we'll have maximum mean temperature and dew point soon. And so you can actually select the period you want to have for the distribution of the percentile. But for this example, I chose to use 1895 to present for the April through October precipitation. So this was through, this map is showing 2020. And we see that, overall there are some drier areas, but there's a lot of areas in the long term that were sort of near average, or even wetter in parts of Pennsylvania and New York. But one area that does stand out is the Adirondack Mountains in New York, and you see some of these drier grid cells showing up as less than the 5th percentile. And so then you might ask, well, just how dry was it? We see it's in those lower percentiles, but how does that compare? So what you can do then is you can actually just zoom into that area I highlighted before, which is shown here on the left. And you can go to then switch over to the time series option and drop a marker in there wherever you want. And so I dropped it in that little bullseye of 0 to 2 percentiles. And then you can just plot the time series of all the April through Octobers going back to 1895. And so we do see indeed that it was in that lower percentile. It was the 4th driest on record here in 2020, which comes out to the 2nd percentile. And it was almost as dry as some of those driest years that were in the 60s, where we saw a string of very dry years in this part of the Northeast. So next I want to talk about a few of the remote sensing products. One is the MODIS land surface temperature. And I think Imtiaz will mention this as it's used in the Larry as well. And so these are the land surface temperatures, which is different from what we would see with, say, the GridMet temperatures, which are the 2-meter temperatures, the air temperatures. And so this is the actual temperature of the land surface that you can look at. And the anomalies can tell you a lot about drought, where you have higher land surface temperatures, you have a hotter land surface, typically lower evapotranspiration and drought conditions in those areas. And so this was the growing season land surface temperature anomaly for 2020. We do see a lot of areas with above normal land surface temperatures. Another feature that was recently added to Climate Engine was the ability to plot the spatial trends. And so, I looked at this map on the left, and you can say, well, how has that changed over time? And so you can select a period, so April through October, and plot the trend spatial. So for each grid cell, it's taking that 20-year time series and computing the trend in degrees Celsius per year here. And we see a pretty strong warming trend in the land surface temperature over that 20-year period. And so another option you can do then is, so when you look at a trend, you got to be a little cautious, especially if it's a shorter period of record. And so you do also have the option then to mask that based on p-value or the significance of the trend. And so what I've done now on this slide on the lower right is only showing the values with a p-value of 0.05 or less, or 95% confidence. And we see those areas in parts of New England mostly that had a stronger trend are indeed significant trends. And so that's a nice feature if you wanted to do a quick spatial trend analysis in Climate Engine. And last product I wanted to mention was field scale vegetation monitoring with Landsat using the normalized difference vegetation index. And so with MODIS, that went all the way back to 2000, and Landsat we have all the way back to 1984, so you get a bit of a longer period of record. So what I'm showing here on the left, and so as I mentioned, you can use the transparency bar in Climate Engine to actually look at the map. And so I zoomed into an area in Vermont in the Lake Champlain Valley south of Burlington that is a ag area. You can see the ag fields here outlined, and then on the right is the map of the percent difference from average NDVI. And so the NDVI gives you a measure of vegetation health or greenness. So higher NDVI would be greener, and lower would be browner or less healthy vegetation. And so we do see in 2020 for the summer NDVI that in these fields it is showing below normal NDVI, and I highlighted a grid cell there that says it's about 12.5% below normal. And so, what does that really mean? What does it look like through time? You can then again go dig in. And so I clicked on that grid cell and then went to the time series, and you can plot the summer NDVI through time. And so this is 1984 to present, June, July, August, mean NDVI values. This line separating the green and the yellow bars is the mean. And so a few things stand out. We do see 2020 was lower than that average. And so if you do know about your own region, you might know about this specific field, you can then say a lot more. But just looking at this, we don't know necessarily if that was a drought impact. It could have been a drought impact because we see other years in the past were higher in NDVI, although 2016 was pretty high, and so it doesn't stand out in that sense. Then you look back further in time and you see these, for an ag field, the summer NDVI is going to be high. It's going to be 0.7 to 0.9, and you see all these values in the early part of the record, 0.4, 0.5, and so it makes you wonder, was this not a farm back in that time period, and was there a different land use? So you can start separating these different types of drought versus human impacts versus land use impacts. Then if we zoom in even further, this is now showing the daily NDVI, or from Landsat, it's once every 8 to 16 days from April 2021 through present. And so we see the seasonal cycle where it's high in the summer, and then when it's snow covered, it goes to these negative values, which really don't mean anything from NDVI perspective. But what we can see are these dips in the summer. Oops, sorry about that. These dips in the summer are actually cuttings or harvesting of a crop. And so I don't know what was planted there, but you can see that in 2020 there was what appeared to be one cutting, and then something happened in the middle of the summer where they didn't seem to get a full cutting, and then it grew back to full greenness later in the summer. Whereas this year in 2021, there were 2 full cuttings already, and it looks like they could get a third crop or a third harvest. And so was that a drought impact? We don't know, but again, if you know more about your specific area, you can make more conclusions about these data. Okay, so now what can you do with the data? How can you access on your own? And so for any of the maps I've been showing, or any maps you make, you can draw a rectangular box and export them as a GeoTIFF, which can be used in ArcGIS or something similar. You can also download them as a PDF, which basically takes a screenshot of the image. And I showed a bunch of time series. So with any of those time series, you have the download button here on the top right, where you can download that picture as a PNG, a JPEG, a PDF, or an SVG. And then you can also grab the data too, and you can download that as a CSV or an Excel file. And so lastly, I did want to mention that there's an API in development with Climate Engine. This would allow you to automate and write code to access some of this, on a daily update type of status. And so the example I wanted to highlight is what drought.gov is actually doing with Climate Engine. And if you go to their current conditions page, you'll see they have some of these 7-day totals, 30-day % of normal, 60-day % of normal for precipitation and temperature, and some of the drought indices. And so they're actually using the Climate Engine API to hit Climate Engine each day and get those pre-computed values and use them in their own web development. And so at this point, the API is still in development. If you are interested in obtaining an API key, please let me know, and we could help you get that and perhaps do some testing of this API for us, like drought.gov is doing. And so I'll just wrap up by saying there's a lot more available. It's kind of overwhelming sometimes what's in Climate Engine. Here's our landing page. There is a user manual, a very detailed user manual with examples. There are global data sets, as well as the seasonal forecasts, which I wasn't able to get into today. But I will end there, and we will hold questions to the end, and I will pass it now over to Mike. And Mike, you should get that now.
Okay, okay, you see my screen, and let's turn to presentation mode.
Yep, looks good to
Okay,
me.
Excellent. Great, so thanks for that, Dan, and for a few plugs in there for EDDI, but here we go, diving into a bit more detail about what EDDI is, the Evaporative Demand Drought Index, and what it can do for the Northeast region. Dan's already introduced the team, and here we are again with our salad of logos. What I'm going to do here is quickly go through some background on EDDI and evaporative demand that underpins it. So basically what EDDI is, how it's estimated, how it works and what it can be used for, and how you can find out more, and how you can find and download the data and the maps for the Northeast DOs. So let's get going. So this then, oops. Advance the slides. I want to advance. There we go. This is the most familiar iteration of EDDI, what EDDI looks like most familiarly. And it's a map of the Northeast DOs, clearly, with counties and states. And you'll see that there's some various labels and timescales indicated. So what EDDI is, in a nutshell, it's the anomaly in evaporative demand, which I'll talk about in a second, at a specific timescale, mapped across given locations, and it's all expressed in percentiles. So this here then is the 1 month EDDI, which means actually 30 days, because an EDDI month is they're all 30 days long. So this 1 month EDDI then, I downloaded it yesterday, and it covers a period from August 11 to September 9, 30 days. It was released, like I said, it was released yesterday, but it was for September 9th, so there's a lag of 4 days. That's because the driving data aren't available for 4 days. We have a bunch of different timescales. There are 24, 1 to 12 weeks, and 1 to 12 months. So from really super dynamic weather scale out to above seasonal scale, annual scales. And it's mapped in terms of warm colors down here, which are the drought categories, which match very well to the US drought monitor drought categories, the same colors and same percentile breaks. And on the opposite side, we have wetness categories, which are at the flip side. Okay, so what does this map show us, for example? So here we see, in northern Maine, for example, we see evaporative demand is unusually high. That indicates drier than normal surface conditions and the atmosphere. There's a connection between the surface conditions and the atmosphere. And that's what we're seeing in northern Maine, and an actually more intense drought in the Lake Champlain area of Vermont and New York. And you'll see here, this is ED3, which if you go down to the key, is between the 98th and 95th percentile. So you would expect to see these conditions only 5% of those periods, those August 11 to September 9 periods. And EDDI is based on a time series of evaporative demand, goes back to 1980, so it's over 40 years long right now. And on the opposite side here, you see in Eastern Connecticut, it's wetter than normal. Okay, so backing out a little bit further, what is evaporative demand? So you may be familiar with the expression PET, or a potential evaporation, or reference ET. So what we talk about here is reference ET. It's evaporative demand is an umbrella term that's given to reference ET, potential ET, and pan evaporation. It's not evapotranspiration. It's not the actual flux. It's the demand in the atmosphere for moisture at the surface. So it's used for crop water requirements, irrigation scheduling. It's used in land surface models, but we're using it here for monitoring drought. And we're using a physically based estimate of evaporative demand. We're using the Penn and Monteith reference ET equation. So simply, you can think of evaporative demand as the thirst of the atmosphere. And it makes sense that the atmosphere and the land surface are linked. When the land surface is drier, the atmosphere is more thirsty. That's the sort of in a nutshell. So how do we use it to measure drought? Well, historically, drought is an imbalance between supply and demand for the surface moisture. But historically, we've estimated the evapotranspiration, the return flux of moisture from the land to the atmosphere, as a function of temperature, which is not a good estimate. What we're doing here is replacing that with a demand that's physically based. It's a function of these variables: temperature, specific humidity, wind speed, and solar radiation. And it's more physically driven by soil moisture status at the ground, where evapotranspiration is physically driven by surface moisture status and evaporative demand. Okay, so boiling this down to the land surface fluxes and states that we're interested in, we see that as time progresses, if you think about this graph in terms of time running from left to right, as time progresses through a drought, so a drying anomaly, precip can decline and meteorological anomalies force drying, whether it's through excess temperature, sunshine, wind, or lower humidity. Evapotranspiration, which is the actual flux, can rise in terms in response to that elevated evaporative demand, and then crash as soil moisture dries out. There's simply no more moisture available. But evaporative demand always increases in drought, which makes it so the response of evaporative demand is often detectable earlier than that of soil moisture, which can make evaporative demand a leading indicator of drought and of flash drought, as we'll see. Okay, so how do we then estimate EDDI? First of all, we start with generating a time series of evaporative demand, and we use, like I said, the Penman-Monteith reference ET. It encodes radiative forcing and advective forcing. The details aren't that important here, but here you see a map of evaporative demand, mean annual evaporative demand across CONUS, across the continental United States. And clearly, it makes sense. Evaporative demand is higher if the atmosphere is thirstier, where it's hotter, windier, sunnier, or drier. And up in the Northeast, it's not those things, so it's lower than in other areas of the country. So we take that evaporative demand. This is to calculate EDDI. We take that evaporative demand reanalysis that's driven from NL-2, temperature, humidity, wind speed, and solar radiation. We calculate reference ET from it, and there's that map again. And then for our period of interest, we aggregate evaporative demand at each pixel in the data set. And if it's a month, then we aggregate 1 month's worth of evaporative demand, and we compare it to that same month over the entire 42, well, this is an out-of-date slide, 42-year record. And we convert that into a standard normal distribution. So where anything on the left side of the bell curve is wetter than normal, the bell curve is absolutely normal, and anything on the right side of the bell curve is drier than normal. And that's what we evaluate as EDDI. So EDDI then, here's that bell curve again. The extremes on the dry side are ED4, that's over 98th percentile, so it would only occur 2% of the time. And the extreme wet would only occur 2% of the time as well, and that's EW4. And that's calculated for each pixel, so we can map it across CONUS. As you see here, this is a 2012 drought. So how can we use EDDI? Well, for a start, the first thing to note is that eddy is multi-scalar. Like I said, we have these 24 timescales. Here I've just picked out 9 timescales for the same date. So this is September 9th. I made this graphic yesterday. And you can see that eddy operates differently at different timescales. This is the last week of eddy in the Northeast. This is the last 2 weeks and the last 3 weeks. And here you're really probably seeing you're seeing Hurricane Ida. It sweeps up the coast of the Northeast, and it's just dumped a bunch of rain, and it's made the atmosphere moister than normal over that 3-week period. But if you move down to the 12-month period, you're really seeing the effect of that 2020 drought, or the remains of the 2020 drought, where it's ED4 up in northern New England, northern New York and Vermont, and it's drier than normal almost everywhere through the region. So it captures, eddy is multi-scalar, and it captures different drying dynamics that operate at different timescales. So the optimal timescale is specific to your region, your season, and your sector. So for example, Zia showed us last week that, for example, the 1-month eddy is strongly correlated with crop yield for corn and silage in New York, New Jersey, and Pennsylvania. But these are state averages with a correlation of 0.6 or more. So some regions will be much more strongly correlated. Like the optimal timescale can vary through seasons and regions. The strongest correlation to crop yields of corn and silage in New York is for the 2-week to 1-month eddy, and it's in May, for example. So these are just examples to show that regionally and seasonally and sectors affect, regions, seasons, and sectors affect what the optimal timescale for you would be. So for crop yield, they're generally around 1 to 3 months. So what can you use eddy for? Well, you can use it in farming, ranching, which obviously we're not doing in the Northeast, but also for hydrologic drought, for fire risk monitoring, and for ecological drought. But what eddy is not a measure of meteorological drought. There's no precipitation input into eddy. For that, you'd want to look at the standard precipitation index, standardized precipitation index. So just some maps to show how eddy looks at the agricultural drought. Here we see that eddy, which is this top right one, this is a 3-month eddy, really picks out the sort of 2 lobes of drought in the west that the USDM captures here as well, and it captures this eastern drought. This is in 2002. You know, it's offset to the north compared to the US Drought Monitor, but all these maps are agricultural. These 3 maps are agricultural evaporative related drought indices, and they all look very similar. They don't look identical, and we wouldn't want them to look identical because they all bring different information to the table. So it shows similar patterns to the US Drought Monitor and other agricultural related metrics. So for early warning drought, this is one of the big selling points of eddy. It shows early warning of drought. And this is not in the Northeast, of course, this is the Midwest drought. And you can see the progression of this is 2-week eddy from May through August during the drought. And you can see this rapid explosion of very dry conditions through July, and then in August that were observed in the 2-week eddy, whereas the US Drought Monitor lagged behind significantly. But the US Drought Monitor didn't have eddy as an input at this point because eddy hadn't been developed in 2012. This is just retrospective. So it leads the US Drought Monitor in identifying flash droughts in general. So what about the flash drought that occurred last year? We talked about this in a bit more detail last week, but here, if you look, this is sort of a film strip of eddy and the US Drought Monitor, starting in February over on the left to September on the right of last year, 2020. And you can see the US Drought Monitor is perfectly neutral until about June, where you see abnormally dry conditions showing up. But what you see in eddy, or the 1 month, the similar dates, is you see elevated evaporative demand in southern New England and the southern DEWS region in mid to late winter. Then you see a wet April, and then you see drying onset again. And it very rapidly deepens in July, August, and September through ED4 all over the region. And US Drought Monitor catches up slowly. I'm not saying that by any means, I'm not saying this replaces the US Drought Monitor. It's a leading indicator that is now being incorporated into the US Drought Monitor. So let's keep going. So on to how you can use eddy as a tool. One of the things that we've done is do these change maps. And you might have seen these in the US Drought Monitor. These change maps. This is between a 2-month eddy timescale over how much did that 2-month eddy change from June the 16th to August of 14. That's a 60-day period. So this is a 2-month eddy changing over 60 days. Then this is that same flash drought period. And you can see this very rapid, if you look at the change maps, you can see this very rapid intensification in central New York and Pennsylvania, and over here in the Rhode Island, Massachusetts area. And this shows a number of categories of eddy that the drought deepened by, the drying tendency, during that period. So this is a sort of an ongoing taking the pulse. How much is eddy changing? How much is the atmosphere drying over any specific period? And I produce these maps for a bunch of different timescales and a bunch of different change periods. And it only shows those periods that either start or end in drought. So like I said, you can see these at, this is 3 maps for the same thing, the same date, September 9th, at a bunch of different time scales. So here's a 1-week eddy, which is sort of weather scale eddy. It only looks at the last 7 days. And over here is a 12-month eddy. How does 1 year compare to 1 year eddy compare to last month's 1 year eddy, for example? This is a long memory thing, and you see a lot of wetting in, now compared to where you stood on September 9th, 2020. So these maps are all available on a website I will show you in a minute. So for general information about eddy, if you're interested in eddy, go to this NOAA webpage. You can just Google eddy NOAA, and it should take you there, or you can email me and I'll point you there. And it's got current CONUS maps, and it doesn't have a synopsis for last week's conditions. Instead, we've replaced it with those change maps, which seem to be get more play with stakeholders. It has an archive of CONUS maps back to 1980 for a bunch of different timescales. You can generate time series of eddies if you have a user selected rectangle. That's on one of these other pages. There's a bunch of team biographies, and there's this very handy user guide that's available on the resources tab. Jeff Lucas and the Western Water Assessment put this together, and it's a very user-friendly step-by-step guide through what eddy is and how you can use it. And more specifically, so more specifically, how you can get it from me, if you're interested in getting specific regions or formats or values added to the maps, I can do that for you. For example, here we have South Dakota has, for some reason, they wanted to have their towns and major highways shown on the map. The Rosebud Sioux here wanted to show the reservation boundaries on the map. Washington State wanted to show I think these are Huck 2s, Huck 8s, I think, or maybe Huck 6s across Washington State on their map. Or you can just download the raw data, either as, in this example, as the actual eddy values, the normal, the standard normal ordinates of eddy, or the categories that converts to. And you can get them at these places. This is that web page I showed you earlier. Like I said, you can just search for eddy NOAA. You can get an over 40-year downloadable archive of CONUS-wide eddy maps or data at this website here, which you don't have to scribble down. I will email. You can email me and I'll send it all to you. Or you can get specific maps for the Northeast News region at this website here. Again, I can pass these on to you. And you can also find it on a bunch of different off NOAA sites at drought.gov or NIDIS news pages or various climate dashboards. If all else fails, just email me, mike.hobbins@noaa.gov, and I will point you in the right direction. And I think that's it. Thanks so much for listening.
Thank you very much for that, Mike. As I mentioned before, we're gonna hold all the questions until after Imtiaz, and then hopefully have a good Q&A and discussion. So I'm gonna pass the baton here to Imtiaz.
Well, great. Thank you, Dan. And greetings, everyone. I'm just going to make sure to show my screen. Hopefully you can see my screen and my slide in the presenter mode.
Looks good.
Great. Thanks, Dan. So I'm going to talk about 2 different web-based tools that Dan mentioned earlier. I'll start with the Landscape Evaporative Response Index, which is kind of a newish drought index that our team created some time back. It was released in 2018. It was a kind of multi-partner multi-institute effort. I really want to recognize North Central Climate Adaptation Science Center for funding the project, and NOAA's Physical Science Lab for providing the technical capacity and kind of the web platform to make this web tool available. And really want to recognize Leslie Smith, who was kind of the primary person to develop this tool. So what LARRY is essentially a measure of land surface dryness. When Mike talked about EDDI, it was the atmospheric dryness he was talking about. And so LARRY really complements EDDI. We kind of call it its younger cousin, but in a very complementary fashion. So what it's working with is evaporative response and not evaporative demand. And Dan mentioned in his talk that LARRY is based on the underlying data for LARRY comes from MODIS Terra thermal imagery. So mostly it's looking at the land surface skin temperature and deriving the land surface evaporative response. So essentially what it's trying to estimate is the ability of land surface to do ET. So based on its mathematical design, it's really that the measure of how moist or dry land surface is, and related to that, its ability to do ET, evapotranspiration. The time period of record that we have for LARRY goes back to 2000, so not as far back as EDDI, which is 1979. Applications, almost all that EDDI does should, LARRY should provide some value for those applications. I see that Sylvia's already put the link for LARRY. The coverage for LARRY, the aerial coverage covers CONUS and northern Mexico. The update frequency for LARRY during the growing season, it's weekly. You have both weekly 8-day assessments and monthly updates. But outside the growing season, it's mostly monthly. And again, it's governed by the data available from MODIS. And so we get the best 8-day data, and that is kind of the rawest data that's used. So that's really available at the weekly timescale, and using that data, we get the weekly and monthly products. So quickly, how LARRY is derived. We use the best 8-day MODIS thermal imagery data, which is available at 1 kilometer. That goes into this CBOP model, which is a surface energy balance model that, just calibrates that skin temperature and into evaporative fraction. So which is based on how hot or cold the temperature is relative to a climatological value. It estimates the ability of land surface to do ET, or its evaporative fraction. And that's kind of the primary estimation that's then used, the product of that with a reference ET available from GridMet, a climatological reference ET for that 8-day period, and gives us the actual 8-day ET value. And that 8-day ET is then accumulated at different timescales from months to seasons, and that ET value, those ET data is then taken through the rank-based non-parametric method that we use for EDDI. So Mike explained that in detail. The same exact method is used to derive LARRY. And I must say that because we had the skeleton for EDDI as a web tool, it was very efficient for us to develop LARRY web tool. Apologies for this very busy slide, but all I wanted to show was it's like any other drought index, and you can read LARRY pretty easily in terms of the percentile categories of dryness and wetness. So dryness, shown by the warm color, shows low ET, wetness shows high ET. We also have this gray area here in LARRY, and that's if you're not detecting any measurable ET using our methodology, that goes into gray. And usually you'll see these very dry places on the continent show up gray. but the gray expands and contracts depending on a Larry map, and that kind of shows you, yeah, how there's sometimes very extreme droughts move across the region, but mostly it's in this part of the very dry region of the continent. Another piece to note here is we do provide drought categories using Larry, as Mike showed for Eddie. We do not have LD4 here, so we have LD0 to LD3, but no LD4. Again, from a short period of record, we cannot get into the 2 percentile category. So we get to extreme drought, but not to exceptional drought in the Larry world. Yeah, I think everything else is pretty straightforward if you are used to using other indices. I'll just keep moving. Just want to point to some strengths of Larry. I think the biggest strength is it's the direct observation from the satellite at a very high resolution. So, I mean, you cannot beat direct observation with any model. But as I point out, observations have their own issues. And we believe that although the research is still undergoing, that it has early warning potential from weeks to months in advance. And as I said earlier, it's pretty sensitive, should be, in theory, very sensitive to soil moisture anomalies, and I'll show you some evidence of that shortly. I should also talk about some potential limitation. I mentioned the shorter period of record. It could be an issue, especially in terms of assessing these relative anomalies in terms of how extreme a situation is currently. With remote sensing, the issue of cloud cover and other missing data issues show up, and that definitely adds to the problem of missing data. Yeah, sometimes the issue of latency is greater in Larry as compared to Eddie, for example. So usually it's 1 to 2 weeks in a good case scenario that we don't have the newest data, but it could be sometime more than that. And because Larry is relatively new, we're still kind of looking at the tool, verifying its ability to do drought early warning and other added value. So yeah, as I said earlier, Larry, we expect it to be sensitive to soil moisture anomalies, and here what I'm showing you for the Northern Great Plains region, a comparison of Larry with different model soil moisture data set. And what I'm showing here is the NLS forced soil moisture modeling, model products from different land surface models at top 10 centimeter and top 1 meter. For July 2017, which was kind of a major drought episode in the region. It was $1 billion disaster. And again, basically, this is just to point that Larry kind of collaborates very well with these different soil moisture products. Interestingly, even though these models are forced by the same atmospheric forcing, they show quite a bit of difference in terms of their spatial modeling of soil moisture. There's another way to look at it, just comparing July soil moisture values with Larry. So just 1 month July soil moisture, top 10 centimeter compared to 1 month Larry, and the soil moisture comes from one of those land surface models I showed earlier. This is the NLS NOAA. And just to point that again, just the high correlation between the two. Of course, the question here is, are the model soil moisture good enough? But these kind of corroborations do help to point to, yeah, Larry has some ability to sense land surface moisture conditions. So I want to quickly get into talking about just Larry's drought early warning potential with regards to the recent 2020 drought and were there signals that were of value. And what I'm showing you here are 1 month Larry values from March through June, comparing that to the June 23rd USDM map. And this June 23rd was the first date on which we actually saw any D1 categories on the USDN map. Before that, we only had D0. So if you look at the 1 month Larry, you do see signs of drying as early as March in parts of New England and other parts of the Northeast. And they kind of persisted into April, but really intensified in May into June. And so just looking at this 1 month Larry maps, one can see there were signals of dryness appearing, weeks to months ahead of perhaps when the impacts were started being felt. This is the same kind of map, but now I'm showing 3 months Larry, and just pointing that perhaps there is maybe a little more signal here in terms of the persistence of drought, especially in the region where ultimately the USDM started to show a lot of stress. Again, maybe as early as April, we were able to see a lot of extreme conditions from Larry's perspective developing in April, but really intensifying into May. And one thing I wanted to point was this region in northern Vermont that I also saw in eddy maps that Mike showed earlier. A lot of dryness showed by at least these two indices, but not really captured here in the USDM maps. And I'll get back to that earlier, but just kind of curious why that place was getting mixed in a kind of a big way. And was it a problem with Larry eddy, or was it was something that, because of the remoteness of the location, that did not get captured in kind of the assessment in USDM. So I'll quickly talk about some of the utilities on the web tool. You can, as with Eddy, you can do monthly maps. With Larry, and these monthly maps are available at 1 month or 3 months time scales. You also can get maps for growing season, calendar, and water year. During the growing season, we also have the ability to get 8-day maps, and these you can do it accumulated starting from April 1st all the way to the end of October, or you can do non-accumulated, so you can just get 8-day maps for Larry. And for any map that you can plot, you can download the data as NetCDF. And lastly, Larry also provides you the ability to do time series, so you can select a rectangular box anywhere in the for the region that Larry is available. That's CONUS and northern Mexico, and plot. So these are only monthly data, so you can plot, integrate different months and plot the time series. And so what I've done here for you is plotted a 3-month Larry ending in July for Vermont. And what you will see is a pretty remarkable value for 2020 for Vermont, almost getting to -3 standard deviations. So just showing, at least from Larry's perspective, extreme dry conditions in July, again shown here in the map. And I've just plotted eddy down here, showing you around those times, starting in July, things are pretty high. So evaporative demand was very high, evaporative response was very low. Again, it doesn't show up that strongly on the USDM map. So something to ponder about. Well, I'll change gears quickly and talk about, for the next 5 minutes, this other tool we have called the Drought Index Portal. Again, a multi-institute, multi-partner effort. I wanted to acknowledge funding from Western Water Assessment and North Central CASC. Also want to acknowledge Travis Williams, who was, again, kind of the main person behind developing this product, and advised by many other folks. So I think I must mention that the strength of Drought Index Portal is, just very efficiently, produce data sets, especially time series data sets, long time series data sets, for different indices and ability to compare across for different regions. So a lot of flexibility in selecting a region and getting you a long time series of these data sets. So different indices as part of the portal include all the polymer indices, SPI, SPEI, and EDDI. Also has some of these important climate variables that you can quickly download using DRIP. So Drought Index Portal, short is DRIP. I know there are other DRIPs out there, and so this is our DRIP. Let me get to the regional selection. Just a pretty flexible and nimble in selecting different regions. So you can select state and county very quickly. You can also do polygons, user-defined polygons, and then it has a shapefile option. You can insert your shapefile and it'll extract data for that. Also very flexible in terms of time selections and doing particularly these time series and mapping. But mapping is not as cool as it's in the Climate Engine tool. But one of the main purposes for this was to help with research, and so yeah, I mean the ability to download time series data is facilitated here. Just want to mention the main primary data source comes from the West White Drought Tracker, courtesy of Desert Research Institute, except for EDDI data that comes from the NOAA site that Mike talked about. And the update of all these data sets is on a monthly timescale. So just a quick glimpse into what you can produce, and you can produce these cool graphs, these long time series, and here I'm showing Polymer Drought Severity Index for the Northeast RCC region. Again, a long perspective of drought really helps, and so it can put into perspective where our current drought is in context of some very historical drought. Polymer drought is very sensitive to long-term trends in precipitation, and you kind of see it here that in the Northeast region, it kind of shows that wetting trend and less of these extreme drought persisting, again, from the lenses of Polymer Drought Severity Index. Same thing I could do with any other indices available. Here I'm showing a 3-month SPI, kind of the similar message, more green than brown, which is dry. So again, showing a wetting trend in the region. On the other hand, if you look at the Evaporative Demand Drought Index, you see kind of a different trend, and we're really trying to see more. And as it's getting wetter, the temperatures are also rising, and that's in part, I think, maybe in the main part, contributing to the increases in evaporative demand, and you kind of see it in the EDDI trend, which is like more positive, more dry. Another thing, very cool thing you can do with DRIP is you can plot these time series in the USDM categories. You can take any of the drought indices and plot them in USDM categories, and not only stop at 2000 where the USDM stopped, but go all the way to 1900. So here I've taken 3-month SPEI and just plotted in the USDM categories using the categories recommendation that USDM provides on its website. You can also quantify for a particular month, you know, area in different drought categories. And so that's just, again, very efficient way to quantify that kind of information. Here I'm showing, comparing just for the Northeast region, USDM and other drought indices for the same period. And this is another cool way to compare, you know, USDM and these different drought indices, how they look like in kind of a USDM space or colors. Or you can also do a calculation of drought severity coverage index. Again, some may really find it useful, but again, it's the product. It's kind of the integration of how much area is in drought and how extreme the drought is, and again, very quick quantification of that metric for any particular month that you're interested in. And I'll end with this specific information that very soon on DRIP will also try to include ability for the user to kind of get the data on projections of these different drought indices at a 4 kilometer spatial resolution. Yeah, so we are developing tools using the MACA V2 metadata downscale climate projections, which has about 40 models, 2 emission scenarios, moderate and high emission scenarios, and time period going all the way to 2099. So, you know, we have plans to basically for the indices available at on DRIP, but primarily SPI, SPEI, and EDI will have these projections available. So, you know, maybe it would be useful to a user like yourself who are interested in exploring scenarios of future drought trends. So that's all for me, and thank you for listening. I'll hand it back.
Great, thanks so much for that, MTS. A ton of great information there, and thanks, Mike. And I think we're going to move on to Q&A. Looks like we have quite a few questions in there, and I think we'll try to get to as many of those as we can. And there is Sylvia.
Hi again, everybody. It's been busy in the chat box as well as the question box. Let's jump right to it. I'm going to start with Carlos Velasquez. Carlos raised his hand very early on in the presentations, but I didn't see his question until later, or maybe he has two. Carlos, I'm going to unmute you if you want to go ahead and ask your question.
Can you hear me?
It's a bad echo, Carlos. He's self-muted. Maybe he'll come back. Hang in there, Carlos. I will go ahead and start with a couple other questions. And I think we'll start with Glenn Kohler's question. Can you generate a trend for number of days per year over 90 degrees Fahrenheit? And I believe this came in during the, was that your presentation, Dan, or was it Mike's?
Yeah, I did show a trend map for the land surface temperature. Yeah, so with the spatial trend analysis in Climate Engine right now, you basically select a time period, whether it's a month or a week or a year period. I don't think we currently have the option to select thresholds, but that would be a great addition. And I will just mention that part of how we get these new things into Climate Engine is just like things like this. We hear these ideas and get requests from users, and we do incorporate them in. So I will definitely note that and bring it up to the development team. So thank you.
Yeah, Glenn also asked if there was any chance of getting an EDI or an ESI forecast map for week 1 month, 2 months, etc. Although I think Mike might have answered part of that.
So I don't do forecasts. EDI is ongoing monitoring, so it relies on reanalysis data that assimilates observations into like a surface map. But I think Dan's shop is looking at forecasts of EDI, so I should actually let him answer.
Yeah, so I did mention we have the CFS downscaled climate forecast system downscaled from 1 to 4 weeks, out to 1 to 4 weeks in Climate Engine, and we do actually have EDI forecasts in there. Yeah, I didn't have time to cover everything that was in Climate Engine, but if you do go to the forecast section in the drop downs there, you can find weeks 1 to 4 separated out by week if you want ensemble median EDI forecasts.
Got it. And let me just stick with Glenn's question. When we got to Larry, his question is, what soil depth is Larry tuned to or best represent?
Yeah, that's a great question. So Larry's based on the land surface temperature. That's really looking at the kind of skin thickness, which is about 5 centimeters. Our sense is that it's more sensitive to all that part of the root zone that is involved in ET process, because that ET's the whole of ET fluxes, which is maybe going down all the way to the root, is influencing land surface skin temperature. So I would imagine like at least from 0 to 40 centimeter, if not more. But we see skills at the depth as deep as 1 meter.
Got it. And let me try to unmute Carlos one more time. And if not, I did get at least one question for him, which is an interesting one. Carlos, I'm unmuting. We'll try it one more time. Looks like that's not going to work today. The one question that Carlos did get into the chat box is a really great one. Could drones help us get data with better resolution so that the indicators are more accurate? Whole team, try it.
Yeah, I mean, that is, of course, a great idea. And I know that drones have certainly been used at the research scale for mapping individual fields, and also some snow mapping is being done with drones. It gets very challenging to scale it up to a larger level to incorporate into something like, you know, a national scale gridded product. But yeah, certainly drones can tell you a lot about the land surface at very high resolution. And I know it, yeah, at the research level, they're certainly being used.
Yeah, and I would say, speaking from the perspective of Eddie and the evaporative demand, I think the increased resolution that would be afforded by using drones would be wasted on a product like Eddie, where it relies on a well-mixed boundary layer, and so it has this sort of spatial averaging effect anyway. You wouldn't pick up much more information. Granted that Eddie's at 12 kilometers, so we would like to go to a finer resolution, but not necessarily to the resolution afforded by drones. I think they wouldn't help.
That's a good one. And we have Vicky Zelte, who was unable to stay with us for the Q&A session, had to leave, but she did leave us several questions. First of all, and I think this goes back to the time of Dan's presentation, can data behind the selected GridMet products and maps be downloaded for additional local processing by local drought regions? A lot of our Northeast states have drought dashboards where they're processing or at least displaying some data. So that's a good question from Vicky.
Yeah, that's a great question. And if you just want to use it for a one-off, yeah, any of the data in there that I was showing, you can download. Time series, you can get the entire period or record for any GridMet variable. We do have a bunch of different polygon regions in there. We have state level, county level, climate division, along with a few other different regions. So yeah, I would encourage you to check out the time series options available in climate division, because we do have a bunch of those regions. But if you wanted it for something like a dashboard, like I showed there in the end with the drought.gov example, that's where the API would be extremely valuable. So you can basically send a call to Climate Engine each night if you wanted to update your drought dashboard. And you know, the calculations are already being done in Climate Engine. So you're basically making a call and saying, I want the 60-day % of normal precipitation, and Climate Engine does the calculation and then returns the grid for you. So again, if you're interested in the API, please contact me or one of the other Climate Engine folks.
Vicky also asks or states, we found false positives for Eddie. It must be considered with SPI and the other indices. It can certainly warn a flash drought when precipitation is already low, but at times high precip and high heat, and that will result in a false positive. So I'll hand that to Mike to sort out.
That's absolutely true. So Eddie does not have any precipitation input. So if you have a hot period and you get a significant pulse of rain during that period, you will get an elevated eddy that is not necessarily reflective of a drier ground surface, but is just reflecting the heat, the heat wave, if you like. So I would, particularly in the Northeast, where you have a more energy limited environment, as opposed to a water limited environment in the West, I would take a flag raised by Eddie as a potential. Potential exists for drought, not you're in drought. It's definitely a potential rather than a warning. She's absolutely right. Yeah.
So I think I'll finish up with one more of Vicky's questions and then we'll move on. Could low AET from Larry mean that it's cooler weather than normal rather than drought? And how can you distinguish that?
Yeah, low AET would really mean that the land surface is very hot. So it would not point towards cooler conditions, because again, Larry's looking at land surface temperature values and seeing how enormously high or low it is from normal. So very high temperature values should give you low AET. And so it should point to hotter conditions and not cooler conditions.
Okay, got it. Next, some questions. Art Degatano, I can't quite see if Art's still with us. Art asked, what happens if a field is fallow in one year and in corn the next? He thinks that the crop type would impact NVDI quite a bit, and this obviously can change from year to year.
Yeah, that's very true, and that's part of why I showed that example of the time series. Yeah, one thing I wanted to emphasize with that was for the NDVI example I showed, this is really valuable if you know a lot about your specific region, even down to your field level, and you wanted to dig in a bit more how it relates to the climate information. Because yeah, certainly if you have a different crop, or as I mentioned, if say at the early part of the Landsat era, it wasn't even a farm at all, it might have been a forest or something else, all that stuff would change the NDVI values. So it can be tricky interpreting unless you know exactly what the land cover and land use is. So that's a great point.
Okay. Let's go to a question from Jeffrey Zimmerman. Jeffrey asks, are Esri web mapping services available for Climate Engine?
I don't think so, and I'm not sure I know enough about that to really answer that. That might be an API related thing. So, and if this person wants to chime in, Sylvia, I don't know if they're still on, but I'm not sure if I can answer that question really.
Jeffrey, I think I see you're still on. I'm going to unmute you. And you might have to hit your unmute button as well. But Jeffrey? I'm not sure if he's still on.
So I'd say as far as I know, no would be the answer to that.
Okay. Let's go to Eric B has a question, although he's left, but we can certainly record this answer. Are the 3-month indices on a 1-month step 3-month running average index? Is that for? Are the 3-month indices on a 1-month step, i.e. a 3-month running average index?
Let me maybe answer both Larry and Eddie. So those are integrated, accumulated over 3 months for ending in a particular month. So a 3-month Larry or Eddie is really accumulation of 3 months of evaporative demand or evaporative response. And so it's ending in that a 3-month July. Eddie is 3-month accumulated ending in July. It's not average running. It's just
not average.
And to be clear with regard to Eddie, Eddy is updated daily, so that 3-month window advances forward every day. And in fact, for every time scale, it advances forward every day, and those data are posted to the web that I showed in the chat box earlier.
Okay. Checking the chat box real quick here. This is a question from Trevor Hadwin. Trevor asks, can Mike discuss how eddy works in the cooler climates and during winter or non-agricultural seasons?
Eddy clearly operates in the cooler climates. Trevor, I think Trevor is. Trevor, are you in Canada? I'm trying to recall. I'm sorry. I have you in my email inbox, and I'm trying to recall where you're talking about. But so Eddy covers. Well, I have a global Eddy. I did not discuss it all, but Eddy covers from 52 degrees north down to 25 degrees south. So there is coverage in cooler climates, particularly up into Canada. I'm trying to remember what the rest of Trevor's question was.
How does Eddy work in the cooler climates and during winter or non-agricultural seasons?
Right. So in the cooler seasons, so Dan actually has done some work in California to show that Eddy has a signal during the snow accumulation period in the CIRES. Longer term Eddy, like 6-month Eddy, for example, has a strong signal that is then linked to the melt off, so the snow melt in these snow melt driven basins. And that's a very interesting finding because it indicates that snow accumulation is reflected in Eddy in exactly the same way that precipitation is reflected in Eddy. So you get a snow covered surface. It cools. It obviously it's cooler than non-snow covered generally, at least in summer. And the anomaly of evaporative demand over that snow-covered surface is just as valid as the anomaly over soil moisture-driven surface, for example. So there are indications that it operates well in snow-covered or cooler regions. As Vicky pointed out, though, in energy-limited regions where the hydroclimate is dominated by precipitation rather than evapotranspiration, like in the West, you would want to supplement Eddy with other indices that reflect precipitation. And I would say a combination of Eddy and SPI would be good because it reflects both the downward flux and upward flux of the hydrologic cycle that then can indicate drought. So it does work in cooler climates. It's available globally, but you'd have to just email me, and I can point you to that data source. And there is a signal in snow accumulation and snow melt seasons as well that it's useful. That's a very brief nutshell answer. Sorry, Trevor.
And I can quickly add, if I may, that during the shoulder season, it may have value for wildfire warning.
Yes, absolutely. Oh, I didn't even talk about wildfire. Perhaps because wildfire isn't a giant problem in the Northeast, but in the West, Eddy has been used as or is being used in various iterations in wildfire seasonal planning and in sort of ongoing meteorological incidents with regard to wildfire. And Dan has actually done some work on wildfire in California and Nevada and Eddy.
Let's go back. I think I missed this one question from Glenn Kohler. Glenn says, it's great to see Eddy projections coming soon. How soon? Weather forecast based or only driven by climate models? Is Glenn still with us? I can actually let you wrap that. If you want to unmute yourself, go ahead, Glenn.
Well, it's just I'm really thrilled to see Eddy forecast because that's very useful. But is it going to be driven by the near-term weather forecast or is it just going to reflect climate model projections over the longer scale and more, more of a static thing?
Yeah, so I did share a link to an 8 to 14 day eddy forecast. And so what we have in Climate Engine right now is based on the climate forecast system sub-seasonal forecast. So that's essentially a weather model being run out to sub-seasonal scales. And so it's a global forecast model that has the drivers that we need to compute the reference ET and then eddy from those drivers.
Thank you.
All right, we
How
still have
soon?
time.
How soon?
Those are available now, out to 4 weeks.
Oh, awesome. Okay, thank you.
And it's in the chat, and I did post one link where you can find one of those maps. And I should also just mention, I think if you are not registered, so if you click on one of those Climate Engine links, you're probably going to be forced to register first. So be prepared for that.
Okay, and I have another question I think we can get to from Trevor again. And this does answer your question Mike, about whether Trevor is from Canada. He asks, is Larry available in Canada? If not, what would it take to expand this tool northward?
Not currently. It's just maybe slightly north of the Conus region. Some parts of Canada are there, but for now it's not there. I think it just would require more funding and partnership to extend it. I mean, the data is there. MODIS is global data, so you can really take it anywhere. So it's just about the deliberation to get it there. Right now, we need people and resources to do that. But thank you for your interest.
Okay. Let's get one from Keith Robinson. Keith asks, can any of the tools described be used to help identify where more monitoring is needed to improve regional assessment?
So I don't know if the tools themselves could do that, but that's where we like to hear from folks. We did show a lot today. Is there something missing that is needed for the Northeast that is not in these tools or anything that you've seen? And so, but I'm not sure the tools themselves can help answer those questions.
Okay. And Jeffrey Zimmerman adds API would work. I don't know if that's a statement or a question. API would work.
Yeah, and if you want to contact me about that, if you're interested, we can set you up with an API token to start using that for climate energy.
Okay, and we're going to probably wrap it up with this one. It's from Stephen Harkey. Stephen says, on the DRIP, many of the Northeast states are small, and when zooming in to see details, they become just small dots and they lose their detail. Can this be made better? Also, can you download the charts at the bottom of the page? Oh, I guess that's for me, at the page versus the screenshot. So what I would say about the download is that we're going to have the entire recording available. And if that doesn't quite meet your needs, please email me. But let's go ahead and let Imtiaz comment on DRIP.
Yeah, thank you for your question, and thanks for looking it up quickly. That is one of the issue with the spatial plots. I did mention my presentation that Climate Engine would give you much cooler maps if you're interested in the maps. We will actually look into that at some point of time, but our main interest was really getting the time series data and visualizing the time series, and that's why we put more effort there than in kind of improving the maps, because there are other utilities out there which can do a better job at mapping these things.
Okay.
Thank you.
My goodness, I think we just made it through in the nick of time, all of the questions that we have. My apologies if we missed anybody, but I do think this was a great discussion. I hope the folks here in the Northeast now feel like we're not being left out of drought research, and that there's active work going on, so we really can get to that early warning capability. Thanks again so much to Dan and his team, Imtiaz and Mike, for your presentations as well. Please look for this recording on drought.gov shortly, and also the recording from the first session from last week. And we'll also be sending out, you'll watch your email for a constant contact email that kind of highlights what went on, quick little summary, and then a link to the recordings that we've had for the last 2 sessions. So thanks, everybody. Have a great day.
Thank you.
Sylvia, everyone else.
Bye-bye.